In this lecture video, we're going to see an application of the central limit theorem to the sampling distribution of a discrete random variable. Now let x1, x2, and so forth up to x sub n be a random sample of size n from the Bernoulli distribution with success probability p, and let x bar be the sample mean. The Bernoulli p distribution has mean p and variance p times 1 minus p, and so the mean and variance of the sampling distribution of x bar are mu sub x bar equal to p and sigma squared sub x bar equal to p times 1 minus p over n, respectively. Now remember that the Bernoulli random variables x1, x2, and so forth up to x sub n are 0 or 1 depending upon whether or not the event of interest associated with each of those trials has occurred. And so the numerator of the sample mean, which would be the sum of the x's, is going to be the number of trials in which the, quote, success, end quote, occurred. So with that in mind, the sample space of the sample mean is going to be the set of fractions 0, 1 over n, 2 over n, and so forth up to 1. Now let's denote the PMF of the sampling distribution of x bar by lowercase g sub n, and note that the PMF of x bar evaluated at a particular value x, where x is in the sample space, this PMF is given by the probability. Well, it's defined to be the probability that x bar is equal to x, okay? And note that x bar is equal to x if and only if the sum of the x's is equal to n times x. And I'm letting y denote the numerator of the sample mean, the sum of the x's. And so, again, the PMF of x bar evaluated at little x, which by definition is the probability that x bar is equal to x, is equal to the probability that y, which I'm using to denote the sum of the x's, is equal to n times x. And if you'll recall back to when we talked about the Bernoulli and binomial distributions, you'll recall that the sum of independent Bernoulli random variables has a binomial distribution. And so this random variable y has a binomial distribution. And so we get this expression for the PMF of x bar stated in terms of the distribution of y. And so this would be equal to n choose n times x times the success probability p raised to the exponent n times x times 1 minus the success probability raised to n minus n times x. And again, y, the random variable y, which I'm using to denote the sum of the x's, which is the numerator of the sample mean x bar, that has a binomial distribution with parameters n and p. So n trials and success probability p. And so on the following slides, I have plots of this binomial distribution, or of just in general of binomial distributions for several values of n, the number of trials, and p, the success probability. And so let's take a look at these distributions, and in particular take a look at the shape of the distributions, whether they are symmetric or skewed, and if they're skewed, which direction they're skewed, and to what extent are they skewed. And so let's start off with looking at binomial distributions for or with a number of trials equal to 10, and I'm going to let p vary from 0.1 up to 0.9, I believe it is. So here's the distribution when n is 10 and p is 0.1, and so you can see it's quite skewed to the right. Here we have p equal to 0.3. It's still skewed to the right, but not as much. Here we have p equal to 0.7, and now it's skewed to the left. And then we have here p equal to 0.9, and it is very skewed to the left. The magnitude of the skewness when p is equal to 0.9 is the same as the magnitude of the skewness when p is equal to 0.1. They just have different signs. Now let's increase the sample size to 20. And so here we have the PMF of the binomial distribution when n is equal to 20 and p is equal to 0.1. And you can see here that it's right skewed. Now the question I would ask, how would you compare the skewness of this distribution to the skewness of the distribution when n was equal to 10? So we go back here. Okay, p is the same now. P is 0.1, but now n is equal to 10. So do they have the same level of skewness? They're both skewed to the right, certainly, but do they have the same level of skewness, or does one have more skewness than the other in terms of magnitude? And so here, again, this is the distribution when n is equal to 10, p equal to 0.1. And here is the distribution when n is equal to 20, with p equal to 0.1. So I'll let you look at those graphs and make your own determination. Again, let's increase the value, p, from 0.1 to 0.3. And so it's still skewed to the right, but it's not as skewed as when p was equal to 0.1. Here we have p equal to 0.7. It is skewed to the left. And then p equal to 0.9, it's even more skewed to the left. Now let's increase the sample size to 50. Okay, and we see that it is indeed skewed to the right. Here p is equal to 0.1. Now let's increase it to 0.3. And it is skewed to the right, but you know, if all we had was, you know, this part of the graph here not going up to 50, I think we might say that, you know, it might be hard to tell whether or not that was skewed, but you can see a little bit of skewness, and so we are getting a, you know, less skewed distribution, it looks like, as we are increasing the sample size, and that again, that level of skewness also depends on the value of p. Here we have p equal to 0.7, and it's left skewed somewhat or slightly, and then p equal to 0.9. Somewhat more left skewed than when p was equal to 0.7. Now let's increase the sample size from 50 to 100. And so here we have the binomial PDF when n is equal to 100 and p is equal to 0.1. And so again, we do have a right skewed distribution, but it's not nearly as right skewed as when for smaller sample sizes. Here we have p equal to 0.3, and now we're getting a distribution that is where it's very difficult to visually see skewness. This looks fairly symmetric. It's not perfectly symmetric. It does have positive right skewness, but that skewness is somewhat close to 0. Here we have p equal to 0.7. Again, we do have some left skewness, but it's minimal. And then p equal to 0.9, left skewness, more so than when p was equal to 0.7. But much less skewness in magnitude compared to these smaller sample sizes with the same value of p. Now let's look at binomial PMFs when the success probability p is equal to 0.5. And you can see here that we have a perfectly symmetric distribution. If we were to calculate the skewness coefficient for this distribution, we'd find that it's 0. Here we have, and by the way, that's for samples of size 10. If we increase the sample size to 20, again, p being equal to 0.5, again, we have a perfectly symmetric distribution, and so its skewness coefficient would be 0. Here we have the binomial PMF when n is equal to 50, with p equal to 0.5, again, a perfectly symmetric distribution. And then finally, when n is equal to 100 and p is equal to 0.5, again, a perfectly symmetric distribution. And so you're probably seeing some trends, and you probably are getting a pretty good idea of the shape of a binomial distribution for various values of p. When p is equal to 0.5, you would probably expect now, based on these examples, that the binomial PMF is going to be symmetric. When p is less than 0.5, the binomial PMF is going to be right skewed. And when p is greater than 0.5, the binomial PMF will be left skewed. And for a given value of p, as the sample size increases, the level of skewness is attenuated. In other words, it gets closer and closer to 0. And so that is, although not a formal proof of these things, in fact, I might have you look at some of these characteristics for a binomial PMF in one of the labs. But I think that these graphs are very helpful in getting a pretty good intuition about how the shape of the binomial PMF depends on both n and p. Now, why are we looking at this? Well, because remember, we're wanting to apply the central limit theorem to the sampling distribution of x bar. And in the description of the central limit theorem, or in the statement of the central limit theorem, we typically would say that for sufficiently large sample sizes n, the sampling distribution of the sample mean can be well approximated by a corresponding normal distribution. So we have to ask the question, what is meant by sufficiently large? How large does the sample size have to be? In the previous examples, for the gamma distribution, or when sampling from the gamma distribution, and then after that when sampling from a uniform distribution, we saw that the sample size required really depends on the shape of the underlying distribution. When we're sampling from a symmetric distribution, like a uniform distribution, the sample size does not have to be that large at all in order for the normal distribution to provide a very good approximation to the sampling distribution of the sample mean. In fact, we saw that for samples as small as 3, 4, or 5, that would probably be sufficient. On the other hand, if we're sampling from a highly skewed distribution, for example, from a gamma distribution, we saw that the sample size needed to be larger in order for the approximation provided by the central limit theorem to be adequate. And so that is going to be the same kind of situation in this case. The skewness of the underlying distribution that we're sampling from, the Bernoulli distribution, is skewed to the right if p is less than 0.5. It's skewed to the left if p is greater than 0.5, and it's symmetric if p is 0.5. And so the the closer, I'll also say this: the closer that p is to 0, the greater the degree of skewness. As p is closer to 1, the greater the degree of negative skewness. And so we, in order to decide or determine, what sufficiently large means in this context, we do have to take p into account. And so we'll do that coming up in some of the slides. So the CDF of the sampling distribution of x bar, we looked at its PMF. We know that we can express the PMF of the sampling distribution of x bar in terms of a binomial PMF, which is why we looked at those graphs. The CDF of the sampling distribution of x bar, evaluated at little x, again, by definition, is the probability that the random variable x bar is no more than the argument little x. This is equal to the probability that y, which again, remember, y is the numerator of x bar. I guess I could have used a summation of the x's, but that was just taking up a little bit too much space in the slide. So this is equal to the probability that y, the sum of the x's, is less than or equal to n times x. Now, remember that this has to be, the CDF has to be defined at every real number. And so if we were to evaluate this at values of x that are not in the sample space, then of x bar, then we need to account for that. And that is done by using the greatest integer function. So again, this function right here is the greatest integer that is less than or equal to n times x. And I describe that down here. Okay, so again, in order to find this CDF, this cumulative distribution function of x bar, this probability accumulator, we have to evaluate the value of the PMF of X bar at all values of in the sample space, and I will denote these values by k over n, from where k goes from 0 up to this greatest integer that is less than or equal to n times x. And so we're just adding up values of the PMF of the binomial distribution. So what we're doing is expressing the PMF of X bar in terms of the PMF of a binomial random variable y. Now, this expression, I mean, this is not a real succinct, I mean, it's succinctly written, but its calculation is fairly tedious. And depending upon the value of n, I mean, it can, if n is large, then this is going to involve a lot of computations. And we may not want to do that. We may not have time, we may not have the resources, and so forth, to get the exact value. It may be that we can come up with, we can approximate this sum, and if that approximation is sufficiently close, then that would be adequate. So fortunately, when the number of trials is sufficiently large, and again, what we're talking about here is when is this going to be a hassle to calculate? Well, it's going to be a hassle to calculate when n is large. But if n is large enough, we can appeal to the central limit theorem, and we can approximate the true sampling distribution of X bar, which is given by this sum by a corresponding normal distribution. And it will be the normal distribution that has the same mean and variance as X bar itself. And we know what the distribution, we know the mean and the variance of the sampling distribution of X bar. We stated it on a previous slide. Now, getting to this question here, when the number of trials is sufficiently large, the central limit theorem can be appealed to. So in this context, when we're sampling from a Bernoulli distribution, based on the graphs that we looked at, what sample size appears to be sufficiently large for the normal approximation to be an adequate approximation to the binomial distribution, which is the sampling distribution of the number of successes. Well, let's take a look at an example, and we'll see if we can get some information on this in terms of comparing. What we're going to do in this example is we're going to calculate some probabilities involving a binomial random variable, and we're going to use the normal approximation to compute an approximation to those probabilities as well. And because we're going to know the exact values, we're going to be able to compare or assess, compare the exact values with the approximations and assess the quality of those approximations. So suppose that 5% of the widgets in a warehouse are defective. A quality control analyst randomly selects 100 widgets at random and with replacement from the warehouse for inspection. Let X be the number of defectives in the sample. So don't let the fact that we're sampling with replacement throw you. That may seem like an unnatural thing to do when in a quality control type of setting. When we sample with replacement, we're allowing, that would obviously make it possible for the same widget to be selected more than once. That is taken into account when we identify the correct distribution of X. So let's think about this, and let's think about what is the sample space of the random variable X, which again, X is the number of defectives that we obtain in a sample. What is the probability distribution of X? What is the expected value of X? What are the variance and standard deviation of X? And then we want to compute some probabilities. What is the probability that X, the number of defectives in the sample, is less than or equal to 3? What is the probability that X is greater than 3? What is the probability that X is greater than or equal to 8? And so we're going to calculate those probabilities exactly. And then what we'll do is we will use we'll appeal to the central limit theorem, and use a normal distribution to approximate the sampling distribution of x, and then we will evaluate the quality of these approximations by comparing the true and the approximate values. So again, we are selecting a sample at random and with replacement from the warehouse. X is the number of defective widgets in the sample, and so obviously we could get no defectives. We could get exactly one defective, or exactly two defectives, and so forth, up to we could get every time we select a widget, we could get a defective. Okay, so the sample space of X is the set of integers from 0 up to 100. Now, what is the probability distribution of X? Well, this fits the mold of this experiment is a binomial experiment, and X is counting the number of successes if we define a, quote, success to be getting a defective widget. And so X is counting the number of successes. And so we know then that X has or we can conclude, let me put it that way, we can conclude without having to derive anything. We're concluding this just based on the nature of the experiment and how X is defined. We can conclude that X has a binomial distribution with n equal to 100 and success probability 0.05. Now, what is the expected value of X? Well, the mean of a binomial random variable is n times p, and so the mean of the distribution of X, or the expected value of X, is 5. What are the variance and standard deviation of X? Well, you'll remember from your methods class that the variance of a binomial distribution is n times p times 1 minus p. And so in this case, that would be 4.75. The standard deviation of X is therefore the square root of 4.75, which to 4 decimal places is 2.1794. Now, what is the probability that X is greater than, is less than or equal to 3? And what is the probability that X is greater than 3? What is the probability that X is greater than or equal to 8? So let's determine these probabilities. Now, we're not going to calculate the exact values by evaluating the PMF and summing those values up. We could do that, but what I'm going to do is use SAS to compute the values of the PMF and the CDF for various values of X. And now I'm not going to do it for all values of X going up to 100, but at least up to 18, because you can see once I get to 18 to 4 decimal places, the value of the PMF is 0 and the value of the CDF is 1. Now, if we were to show more decimal places, we would see that values of the PMF are a little bit bigger than 0, and the values of the CDF are a little bit less than 1. But to 4 decimal places, this is as far as we need to go. And so to find the probability that the probability in this case that X, the number of defectives in the sample, is, let's see here, less than or equal to 3, all we have to do is look in the row corresponding to X equal to 3, and we're looking in the column for the CDF. And so we see that this probability is 0.25784. Okay, and then, oops, there we go. Okay, to find the probability that X is greater than 3, notice that by the complement rule, this is equal to 1 minus the probability that X is less than or equal to 3. So we would subtract this from 1, and that gives us the probability that X is greater than 3. Then to find the probability that X is greater than or equal to 8, notice that that is the same as the probability that X is strictly greater than 7, and that is equal to 1 minus the probability that X is less than or equal to 7. And so we could go up here and look up 7. Okay, look in the column for the CDF. And so we see here that the probability that X is less than or equal to 7 is 0.87204. And so we subtract that from 1 to get the probability that X is strictly greater than 7, which is the same as the probability that X is greater than or equal to 8, And so we have 0.12796. So these are the exact values for those probabilities to 5 decimal places. Now what we're going to do is we're going to approximate these probabilities using by appealing to the central limit theorem and using the appropriate normal distribution to approximate the sampling distribution of x. So we're going to define a new random variable y, which has a normal distribution with the same mean as the distribution of x, which is 5, and the same variance of the distribution of x, which is 4.75. And so therefore the distribution of y, this normal distribution, has the same standard deviation as x as well, which is 2.1794. So by the central limit theorem, what we're going to do is we're going to approximate the probability that x bar is less than or equal to 3. We're going to approximate that by the probability that y, this normal random variable, is less than or equal to 3 as well. Now, we know that when we compute probabilities involving a normal random variable, what we do is we standardize everything inside the parentheses by subtracting the mean from each side and then dividing the differences by the standard deviation. Now, if we standardize everything inside the parentheses here, then we get the standard normal random variable z, right? When we standardize y, a normal random variable, we're going to get the standard normal random variable. And then on the right-hand side, rounding 3 minus 5 over the standard deviation, which is 2.1794, rounding that to 2 decimal places, because that is the precision, or that's the number of decimal places that we had in the table, the standard normal table that we're using, then we would get a negative 0.92. So this probability is equal to the probability that the standard normal random variable is less than or equal to negative 0.92. And then from the standard normal table, we get 0.1788. Now, depending upon the table that you use, it may give you these probabilities to 4 decimal places, like I've got here, maybe 5 decimal places. When I created this slide, these slides, I was using a table that gave me probabilities to 4 decimal places. But we may have, I have to check and see. Currently, I think the table list gives 5 decimal places. So you'll just make that adjustment or just keep that in mind if you work this on your own, which I highly recommend. Okay, so this is our approximation based on the normal distribution for the probability that the binomial random variable is less than or equal to 3. Now, we're going to evaluate the quality of that approximation. And we're going to do that by calculating the relative error of the approximation. Now, the relative error is equal to the approximate value minus the true value over the true value times 100%. And we found, you'll recall, that the true value to 5 decimal places was 0.25784. And so the relative error of this approximation is negative 30.65%. Now, it's negative because the approximation is less than the true value, right? And but the magnitude is 30.65%. So this is a horrible approximation. Wow, we would certainly, if we're wanting to approximate a probability, we certainly want to do better than underestimating it by 30.65%. Now, because the true sampling distribution is a discrete distribution, we can improve the quality of this approximation by using a continuity correction factor. There are actually 2 reasons why this approximation, 0.1788, is, or let me put it this way, there are really 2 reasons why the normal distribution is giving us such a poor approximation equal to 0.1788. One reason is because we are approximating the sampling distribution of a discrete random variable by a distribution of a continuous random variable. We're going to improve the approximation based on that issue by using what's called a continuity correction factor. The other reason that this approximation is so poor, I will explain in a few minutes. So what the continuity correction factor does is it takes into account that we are approximating the distribution of a discrete random variable with the distribution of a continuous random variable. And the reason that there's a problem here, or that causes a problem, is that, let me back up a second here, by approximating the probability that x is less than or equal to 3, using the probability that y, this normal random variable, is less than or equal to 3, we are excluding half of the rectangle that is of the binomial distribution that is centered over 3. You'll remember that the PMF of a binomial random variable in particular consists of a series of rectangles, or a sequence of rectangles that each are centered over the integers in the sample space of that binomial random variable. And they have a width of 1. And so, for example, the rectangle centered over 3 starts at 2.5 and ends at 3.5. Well, we are, by only looking at by approximating this probability by the probability that y is less than or equal to 3, we're not getting the last half of that rectangle centered over 3. And so what we're going to do to improve, or to correct for that, is to use the continuity correction factor. And so what we will do then to implement that is to approximate the probability that x is less than or equal to 3 by the probability that y is less than or equal to 3.5. And so now we're including all of that rectangle that's centered over 3. And so when we do this, and then go through the same kind of calculations to calculate a normal, or a probability for a normal random variable, then we get a much better approximation of 0.2451. Now, the relative error of that approximation is still not that great. It's still negative 4.94%. I mean, we would really want an approximation that has a or a relative error much closer to 0. Okay, less than 1% in magnitude, if we can get that. But you see that this does improve the approximation quite a bit. The relative error goes from a magnitude of 30.65% down to a little under 5%. Okay, so it's an improvement, but it's still not that great. Well, let's continue on, and then we'll talk a little bit more about why the approximation is still not very good. So we want let's find the probability, or approximate the probability, that x is greater than or equal to 8. Well, again, let's use what we might call the naive approach. Let's approximate the probability that x is greater than or equal to 8 by the probability that y is greater than or equal to 8 as well. Now, when we do that, and then go through the calculations for calculating probabilities from a normal distribution, we get an approximate value, an approximation of 0.0838. Now, the relative error of that approximation is, wow, it's really bad as well, negative 34.51%. So a very, very poor approximation. Now at this point, you might be saying, hold on, you were saying that we were going to approximate probabilities for a binomial distribution using a normal distribution. I don't think I want to do that because these approximations are so bad. Well, we're going to talk about that, and you're absolutely correct if you think that there are going to be certain situations where you would not want to use this approximation. But there are going to be situations where it will give you very good approximations. So we can, again, improve the quality of this approximation by using the continuity correction factor. And let me just say that using this, in this case, using the naive approach, what we're doing is we are excluding the first or left half of the rectangle centered over 8. The rectangle that is centered over 8 starts at 7.5 and ends at 8.5. And so by approximating the probability that x is greater than or equal to 8 by the probability that y is greater than or equal to 8, we're excluding the first half of that rectangle centered over 8, that portion that starts at 7.5 and ends at 8. And so we can improve this approximation by starting at 7.5 rather than 8. And when we do that, then we get an approximate probability of 0.1251, which is much, much better, much closer to the true value of 0.12796. And in fact, the relative error is only negative 2.24%. So it's better than the other probability that we were looking at, the probability that y is less than or equal to 3, but it's still not that great. Now, let's talk about why, even when we're using the continuity correction factor, the approximation provided by the normal distribution is still not very good. To do this, let's take a look at the true sampling distribution of x. Okay, here's the binomial distribution for n equal to 100 and success probability p equal to 0.05. Now I would ask you, does that look symmetric? If we were to superimpose, use your imagination and superimpose a normal curve on top of that, a normal distribution that has the same mean and the same standard deviation, do you think that normal distribution would give you good approximations to that particular binomial? In other words, would areas under a normal curve superimposed over this binomial distribution give very good approximations to the areas of certain rectangles? And I think you would say the answer is no, and the reason is because this distribution still has a fair amount of right skewness. And that's really the underlying problem here. That's why even when we use the continuity correction factor in this particular example, why the probabilities are, the approximations are still not that great, because the sample size is not large enough for the distribution of x, the corresponding binomial distribution, to be as symmetric, to attenuate that skewness to a degree that the normal approximation provides a good, the normal distribution provides a good approximation to the binomial. So that's the underlying problem. So even though so this goes back to that question, how large does n have to be in order for the normal approximation to be adequate in approximating probabilities from the binomial distribution? And in this case, a sample size of 100 is really not adequate in this case. And the reason is because p is very close to 0, isn't it? And if you think back to those graphs that we looked at, the graphs of the PMF, the binomial PMF, that depending upon the value of p, for a given value, for a given sample size, that distribution may have looked symmetric or it may not have. So we really do need to take p into account when we consider the question, how large does a sample size have to be? Now let's look at another example. Suppose that 43% of registered voters agree with a particular government policy. A pollster randomly selects 2,500 registered voters and asks whether they agree with the policy. Let the random variable x be the number of voters in the sample expressing approval for the policy. And so again, we want to answer the same kinds of questions as we did in the previous example. What is the sample space of x? What is the probability distribution of x? What is the expected value of x? What are the variance and standard deviation of x? And then we'll compute some probabilities, both exactly using, I'll get these probabilities, the exact probabilities from SAS, and then we'll approximate them using the appropriate normal distribution. But for example, what is the probability that at least 1,100 voters in the sample express approval? What is the probability that more than 1,125 express approval? And so in this case, the sample space of X is the set of integers from 0 up to 2,500. The distribution of X is the binomial distribution with n equal to 2,500 and success probability 0.43. So just think about it, and convince yourself that this is in fact the case. What is the expected value of X? In other words, what is the mean of the distribution of X? Well, it's n times p, or 1,075. What are the variance and standard deviation of X? Well, the variance is n times p times 1 minus p, and that turns out to be 612.75. The square root of that is the standard deviation. So to 4 decimal places, that's equal to 24.7538. All right, now what is the probability that at least 1,100 voters in the sample express approval, and what is the probability that more than 1,125 express approval? And so we're going to get these values again from this, from the values of the CDF that I computed using SAS. All right, so I've got two slides containing values that we would need. And let's see here. Actually, I guess that's a duplicate. All right. So here are the exact probabilities rounded to 5 decimal places. The probability that X, the random variable X, which is the number of people in the sample who express approval, the probability that X is greater than or equal to 1,100 is 0.16114. And the probability that more than 1,125 people express approval is 0.02081. Now, let's approximate these probabilities using the appropriate normal distribution. That normal distribution will have the same mean and variance as the distribution of X. And so Y is going to be normally distributed with a mean of 1,075 and a variance of 612.75, and so therefore the standard deviation of the distribution of Y is 24.7538. Now, using this normal distribution to approximate the probability, and I'm not going to use the naive approach here. I'm going to go ahead and use the continuity correction factor. Then the approximation that I get from the normal distribution is 0.1611. Now that's very close to the exact value of 0.16114. In fact, the relative error is only negative 0.0248%. Now that's just a little bit more than 0.02% off. And so this is a very, very good approximation. And you would agree that because n is so large, 2,500, to compute this probability by hand with a calculator, for example, and if we had to evaluate the values of the PMF for X equal to 1,100, and then 1,101, and 1,102, and so forth, up to 2,500, it would take forever to do that. Now, if you do have a program, a software package that can calculate these things for you, that's fine, okay? But we may not, in certain situations, have access to that kind of software. But what we're seeing here is that if we had a standard normal table, it would be very easy to get a very good approximation of this probability using the appropriate normal distribution. And we see that the approximation that we get is only about 2/100ths, the relative error is only about 2/100ths of 1%. So it's a very good approximation. Again, using the central limit theorem to approximate the probability that that X is more than 1,125, that is approximately equal to the probability that y is greater than 1,125.5. Notice I'm again using the continuity correction factor. All right, and so then when we go through the calculations, this probability is 0.0207. Now that's very close to the true value, 0.02081. In fact, the relative error is negative 0.529%. So about 0.5% low. And so that is, again, a very good approximation. So in this example, we used the continuity correction factor right off the bat, and we got very good approximations. And the reason that the approximations are so good is not only because we're using the continuity correction factor, but because this is the true sampling distribution of x in this situation. It's the binomial distribution with n equal to 2,500 and success probability 0.43. Now, because 0.43 is fairly close to 0.5 and because the sample size is really large, you can see here that the distribution of x, even though it's a binomial distribution, it looks like a normal distribution, doesn't it? So if we think about superimposing a normal curve, normal PDF curve on top of this distribution, the normal curve for the distribution that has the same mean and variance as this binomial, then it's clear that that normal curve is going to give very good approximations to the areas of rectangles over certain intervals. And so this is why the normal approximation is so much better, just very good for this binomial distribution in this situation. Now, let me give you, I don't have this typed into the notes, but let me just give you a rule of thumb, a very good rule of thumb, or kind of a standard rule of thumb that answers the question, how large does n have to be? And remember, we have to take p into account. The closer p is to either 0 or 1, the larger n is going to have to be. The closer p is to 0.5, n is not going to have to be as large. And the rule of thumb is this. If n times p and n times 1 minus p are both greater than 10, then the normal distribution will provide a good approximation to the binomial distribution. So again, if n times p is greater than 10, and if n times 1 minus p is greater than 10, then we can feel comfortable using the normal distribution to approximate probabilities from the binomial distribution. So this is the final example, the final application of the central limit theorem that we're going to look at in terms of examples. And I believe you've got some questions in some of the worksheets and so forth that use this. So this should be helpful in your being able to do those kind of problems.